Let's face it, human beings are really bad at a lot of things. It's very hard for a human being to set out to do a task and complete it error-free. There is even a term for it, known as human error, which is widely accepted. This also applies to writing code, which is barely ever a perfect process. Software nearly always has bugs. You probably already know that we're not talking about bugs that fly around in your room while you're trying to sleep. That said, the first computer bug was an actual bug, but more about that a bit later. A computer bug is an error, flaw, or fault that causes the program to behave unexpectedly or produce unexpected results. It is essentially the behavior that is observed when a program doesn't perform as intended. This applies to both computer hardware and software. Bugs are typically the result of errors made by the developers during the development process. Errors can also occur when a program is translated from one language to another. What works in one language may not necessarily work in another. Bugs will literally bug you, just like a mosquito would, until you get rid of them. A program will produce unexpected results or behave unexpectedly until bugs are removed from it. The term bug has its origins from the 1800s, where it became popular in engineering circles to term things that were not working correctly as bugs. If you remember from Module 1, early computers used vacuum tubes and a lot of mechanical parts. The very first instance of a computer bug was recorded at 1545, a quarter to 4, on the 9th of September, 1947. This bug was actually a moth, which had a 5-centimeter wingspan and was extracted from the number 70 relay, panel F, of the Harvard Mark II Aiken relay calculator. The bug was carefully removed and taped to the logbook, and the term computer bug was used to describe the incident. The first actual case of a bug being found are the exact words that were used in the logbook. This logbook, complete with attached moth, is part of the collection of the Smithsonian National Museum of American History. The Harvard Mark II operators did not coin the term bug, but it seems as though the incident contributed to the widespread use and acceptance of the term within computer software circles and vocabulary. That said, there is a common misconception that we need to address before we move further. Finding out that your computer has a virus can be a frustrating experience and often causes your computer to behave in unexpected ways, stealing your passwords and wiping your bank account clean. It can make your computer's fans sound like a jet that's about to take off while the CPU and GPU are busy mining Bitcoin for someone else at your expense. It is, however, technically not a bug, because the malicious developer actually meant for your computer to behave like that. A bug, on the other hand, is purely unintentional. It is an error on the part of the programmer. Bugs can turn out to be very expensive mistakes. Take, for example, the Ariane 5 rocket failure in 1996. The Ariane 5 explosion was one of the most expensive software mistakes in history. It was a famous European rocket that was used to launch satellites, and the project cost around $8 billion. The rocket exploded a mere 40 seconds after launch. The rocket crashed because of an integer overflow error, which is a pretty common bug in computer programming. It occurs when the programmer overlooks the amount of memory that is required, which is exactly what happened during the development of the project. The investigation revealed that the code tried to fit a 64-bit number into a 16-bit space. It was a pretty expensive bug, which caused a loss of around $370 million. That's quite a lot of money. Another more recent example is the year 2000. In the 1960s, it was standard practice to represent dates. For example, 1960 as only 60, and leave out the 19. Back then, memory was scarce, and many programmers thought that the first 2 digits in the variable year was an unnecessary waste of memory. It was all roses till December 31, 1999. Then reality hit. Once January the 1st, 2000 came, many computers read the year as 1900 because the 2 digits represented 19 instead of 20. If you're kind of old, you probably remember the bug that was jokingly called Y2K, or the Millennium Bug. It affected banks that calculate the interest rates on a daily basis, centers of technology such as power plants, transportation, and a lot of other things. It was a spectacular show which ran into billions of dollars worldwide as various entities around the world upgraded their systems. Yet another example is NASA's Mars Climate Orbiter from 1988. Due to the different units of measurement, it met its unfortunate demise after traveling towards Mars for 286 days. The project cost about $125 million with the intention of studying the Martian surface and climate. The orbiter lost communication with the Earth station and entered the Mars atmosphere at a wrong angle. Yet it was supposed to orbit rather than entering the planet's orbit. And the reason for this miscalculation? The software that controlled the orbiter's thrusters used imperial units instead of metric units. A quick stop to share another fun fact with you. Did you know that the song Gangnam Style broke YouTube? When YouTube was first developed, nobody thought that a single song could rack so many views that it would exceed the maximum size of the 32-bit signed integer data type, which is 2,147,483,647. When Gangnam Style came out, it racked up a whopping 3 billion views, which exceeded the maximum value on YouTube. Bugs or software defects are typically classified by nature, priority, and severity. Let's look at each of these more closely. We will first look at classification by nature. This refers to how the bug affects the system, and this could be in any of the following ways: functional, performance, usability, compatibility, or security. Functional defects are errors that occur when the software behaves in a way that is not compliant with functional requirements. This type of defect is usually discovered during functional testing. An example of this is of a system that should only accept integers, but is found to accept floating point numbers as well. Performance defects is the term used to describe when the software does not perform at an acceptable speed and stability. This is what is tested for during performance testing. You remember from previous lessons that any software package should be able to use as little resources as possible while having the maximum possible throughput, which equates to efficiency. The software package should also be as stable as possible in the target environment. If, for example, your program only responds 5 seconds after a mouse click, then its performance is certainly not up to scratch. Usability defects occur when a software package is difficult to use or navigate, or is unnecessarily complex. Think of a sign-up process that has 7 stages instead of just 2. These are validated against usability requirements during usability testing. Next, we have compatibility defects. Software packages should show consistent performance and behavior across all target systems. An example of this is a website that doesn't show all elements on a mobile device, but works just fine on a desktop display. Guidelines for websites typically state that the experience should always be uniform regardless of the end user's platform. This is also expected across versions of operating systems. A software package is deemed defective if it works on Android 9, but starts to exhibit different behavior on Android 11. Defects can incorporate things such as what size and type, placement of user elements, and response of buttons, right up to back-end functions. A software package might work correctly but come with security defects. If you remember from our previous module, it is always good programming practice to write code in such a way that the attack surface is kept at a minimum. This includes keeping the scope of variables in check and making sure that elements that are not being used are removed from memory. The software package is tested against known threats and vulnerabilities, such as weak authentication, buffer overflows, and encryption errors. As mentioned at the start of the section on types of bugs, software defects can also be classified by severity. There are typically 4 levels of severity: critical, high, medium, and low. Critical defects are the highest level and should be addressed immediately, since testing can't proceed without fixing these. An example of this is an application that doesn't store input that is required by the next procedure. There is no point testing this package, as there is simply no data to work with beyond the point at which the error has been detected. High severity defects are a level below critical defects. These affect the key functionality of an application. The software package may work in some way. For example, a system that should allow 2 people to log in at the same time only allows one person to log in and use all the functionality of the software package, but doesn't allow the second person to go past login, while the first person is still using this software package. Medium severity defects refer to minor defects. A minor function exhibits behavior that is contrary to what is specified in the requirements, such as an about page that doesn't work. The information contained on this page is still important but does not affect the core functionality of the program. Low severity defects are typically minor defects that the production team can't get away with and release the software anyway, such as text that is not properly aligned. The last aspect that we will look at is bug classification by priority. This has a direct link with the effect that the bug has on the end user, both in terms of productivity and throughput. It is also directly linked to the severity ranking of a bug. There are basically 4 types of priority: urgent, high, medium, and low. Urgent defects need to be fixed as soon as they are reported. These are not limited to severe bugs only, as low severity defects can be added to the list as well. The project manager, product owner, or stakeholder can identify the priority of the bug. Next in line are high priority defects. These are slotted to be fixed in an upcoming release, since the user can make do with the system as it is and wait for a fixed release. These are typically in the software package's exit criteria in the set release. Medium priority defects are the errors that may be fixed after an upcoming release or in the subsequent release. The development team can forego these changes in the current release and take care of them in the next one. Low priority defects are typically not much of a bother and can be dealt with when there is time for them. They don't adversely affect the software package, and the stakeholders are concerned by the bug but don't really put pressure on it to be fixed. Allocating the correct prioritization and severity levels speeds defect fixes and increases the overall capacity and efficiency of the testing system, which in turn streamlines the whole testing process. This is crucial for the milestones and deadlines of the project. It is clearly better to avoid bugs to begin with, and this has everything to do with what we have been learning throughout the course. The key to avoiding bugs is code simplification. It is good programming practice to make sure that your code doesn't try to do too much. The best way of avoiding bugs is to avoid code that has internal structure. In simpler language, A function should do just one thing. This makes it easier to trace errors in a block. This goes hand in hand with modularity. Code is contained in functions and macros. The function and macros are each responsible for a single component of the program. The functions are interconnected using shared variables and parameters. As a programmer, you should make sure that the functions depend on each other in clearly defined ways. Putting code in containers makes it a lot easier to isolate any problems in the code. You can isolate a module and test it independently. Another way to avoid bugs is to use existing libraries. We learned in previous lessons that C and other programming languages allow you to create your own libraries. This comes in handy when you want your code to be portable and yet still have all those clever little ways of solving problems that you created in your code. But that could come with problems. If there is a well-tested library available that will carry out the same function you were planning to code, it is generally better to use that code instead of writing your own code. In many cases, the process of debugging a software package can take more time than it initially took to write the software package. Bugs typically start to pop up in pre-deployment testing and continue right well into the maintenance stage. Debugging is an important part of determining why an operating system, application, or program is misbehaving. Bugs are pretty commonplace, even if you take due care and use the same coding standard as other team members. Bugs will still pop up in your new software package. Debugging applies to both hardware and software. It is a multi-step process that involves identifying a problem, isolating the source of the problem, and then either correcting the problem or looking for a way to navigate around it if it proves too difficult to remove or it simply can't be removed at all. Debugging is part of the software testing process and is an integral part of the entire software development lifecycle. The debugging process involves the following steps. Identify the error. Locate the error. Analyze the code. Prove the analysis. Build the fix. And test and validate. Okay, let's now look at each step a bit closer. Error identification is naturally the first step in addressing a bug, or any problem for that matter. A badly identified error can lead to wasted development time, which in turn leads to missed deadlines and a generally sloppy product. Production errors are typically reported by users and are often hard to interpret, and sometimes the information that the users provide is vague and doesn't really pinpoint the problem. It is important to identify the actual error to effectively solve the problem. After positively identifying the error correctly, it needs to be located in the code. No fancy bells and whistles here. The focus is purely on locating the error. After all, there really is no point trying to fix an error when you don't know where it is coming from. In the third step, the code is analyzed to understand what exactly it is doing against what it is supposed to do. This helps the developers understand the error. There are two main goals in the analysis stage. Checking if the error does not cause a ripple effect, essentially checking if a bug doesn't affect any other parts of the program. The second part addresses the risks of incurring any collateral damage in fixing the bug. The fourth step is to prove the analysis. This stage looks at the bug and all the problems that it is causing and documents it. This information is used for writing automated tests for these areas with the help of a test framework. This means that developers can automatically test for these bugs in future builds of the software. Step 5. Build the fix. The actual code for the fix is then written and appended to the existing code. Step 6 is testing and validation. The entire program is then tested again to see if it now performs as expected. Validation seeks to determine whether added code does not cause new problems. You probably don't want to hear this, but it is quite common that new errors sprout in other places after you fix a known error. The errors might even go unnoticed, only to be discovered by the user after deployment. Before we attempt to use any tools for debugging, it is important to know the basic steps. These steps are extremely general and apply to pretty much everything that needs to be built. They are: know what your program is supposed to do, detect when it doesn't, fix it, and repeat until everything works. It is really just as simple as that. No fancy words and complicated processes. This is the basis of all other debugging methods. A common misconception is that step 1 is not that important, and we should focus on making whatever code we have work in whatever way. Many people just go into the code and randomly change bits of code until it works. While you can certainly get away with this on small programs that just span a few dozen lines of code, this quickly becomes extremely inefficient and untenable when you are working with large blocks of code. If you don't understand one function of a program, it is most likely that you don't understand the rest of it. And you will spend hours and hours of meaningless clicks that will not get you anywhere. Another common trick that people try is to debug the code by just looking at the output. Again, if you don't understand what the program is doing to get to that result in the first place, then you likely are not going to get anywhere just by looking at the output. You are literally just guessing what the computer did instead of going into the code and following along the path that the computer followed to get to that result. These basic guidelines are what you need to use before you start using any fancy debugging tools. As soon as your code starts getting a bit complex, you should make it standard practice to add asserts into your code. You recall the assert header file from our lesson on header files, which gives you access to the assert macro, which in turn allows you to test if a condition is true and halts your program if it isn't. This code snippet shows how you can use the assert macro. This pretty simple assert tests if 1 plus 1 is equal to 10, which is obviously false, so the program fails to get that line and returns that error. Try running it on your own PC to see for yourself. This makes it very easy to pinpoint exactly where the error occurred. If you're using a Linux system, then you're in luck. You can use the GDB debugger to basically follow along as your program runs. Using GDB debugger, you can see exactly what the program did every step of the way. There is some good news for Windows users as well. Some versions of Windows compilers come with the GDB debugging tool as well. When you're working with pointers and dynamic storage allocation, the valgrind program can come in handy. It essentially produces a report of any locations and deallocations that occur in your program. The program can be used with the argument -q so that it suppresses all other output that is not necessary for debugging and only display errors. It can also be used for other things, such as checking for memory leaks, which, if you remember from our previous lessons, can potentially cause security problems after deployment. The places in which all these tools stop when they encounter problems are called breakpoints. A breakpoint is a point in a program where execution is halted intentionally, either by pausing or terminating the program if an unexpected result is encountered. The tools that we've just discussed employ breakpoints by testing for certain conditions at certain points in the program. It is worth noting here that the methods that we discussed are not the only tools that are available out there. There are many debugging tools, even within C programming itself. Each programming language and IDE typically has its own tools that addresses its syntax and constraints. Breakpoints can be set in a lot of variable ways that addresses specific needs, both for the programmer and in compliance with the compiler. Debugging can be thought of as an art. You might spend hours and hours looking for bugs and end up extremely frustrated after not finding them. Here are some pointers on debugging that may prove useful to you. The strategies we're going to look at are automated testing, change development strategy, logging, cluster errors, debugging output, and then change your attitude. Automated testing is widely used in the software industry and is now used in a wide range of projects. Testing is carried out using a testing framework that can test things such as the graphic user interface using recorded keystrokes and mouse clicks that generate known output. This makes routine testing take far less time than it would if it were done by actual humans. API-driven testing validates the program's behavior using a variety of arguments and checking if the results are correct. This is a key feature of agile development methods, as we saw in our previous lesson. Another method of eliminating bugs is to change the development strategy of the software. The incremental and bottom-up approach to program development allows programmers to isolate errors since the program is developed incrementally, and testing is done as often as possible after adding each piece of the project. This has the direct effect of reducing the number of errors that the programmers have to work on at any given time, since a unit is tested before another piece is added to it. Another method is logging. Logging refers to the insertion of a number of printf statements that write to a file called a log. You may have seen such files if you have installed a software package before. At each critical step in the program, a line of text acknowledging the step that has just been executed is appended to the file. This is extremely useful for the end user to pinpoint errors in the deployment environment, especially if the error is due to a conflicting software package that can easily be removed without recompiling the program. If you're a member of the Android beta program, then you'll see that people are often asked for logs if they encounter problems with the software. This allowed the programmers to see exactly what went wrong during execution and the development environment, and therefore it takes less time for them to locate and deal with a bug. If there is a large number of errors that are reported, it is easy to cluster them, grouping them as similar bugs, then examining only one bug from each class. The reasoning here is that bugs from the same class are being caused by one root problem. So, addressing the root problem will probably fix the bug. While it doesn't always work, it sometimes saves developers a lot of time by helping them localize problems. Debugging output is not usually recommended, as it takes much more time to look at the output than just to go back and look at the source code. In Samuel's experience, it is only really useful if you understand the source code that you wrote and know how it got to the output that you're looking at. If you prefer to look at the output, it probably means that the code that you're running away from is not as readable as you think it is. That said, if your output has certain traits or patterns, especially if it is repetitive or has a lot of dependencies that are daisy-chained, you can quickly pick up where the error occurred. And this makes it easier to go back to the source code, since you will know exactly where in the source code you need to go and fix. Sometimes it comes down to simply changing your attitude about where to expect the errors. The bug may not be where you expect it. If a large amount of time has unsuccessfully been spent inspecting a particular piece of code, the error may not be there. Keep an open mind and start questioning the other parts of the program. Ask yourself where the bug is not. Sometimes looking at the problem upside down gives a different perspective. Often trying to prove the absence of a bug in a certain place actually reveals the bug in that place. Explain to yourself or to somebody else why you believe there is no bug. Trying to articulate the problem can lead to the discovery of the bug. Be sure to inspect input data and the test harness. The test case or the test harness itself may be broken. One has to check these carefully and make sure that the bug is in the actual program. Make sure you have the right source code. You must ensure that the source code being debugged corresponds to the actual program being run, and that the correct libraries are linked. This usually requires a few simple checks, using makefiles and makeprograms. For example, the compilation manager and .cm files. They can reduce this to just typing a single command. Take a break. If too much time is spent on a bug, the programmer becomes tired and debugging may become counterproductive. Take a break. Clear your mind. After some rest, try to think about the problem from a different perspective.